everybody. Welcome to the spring series of Quantum Thursdays. As a reminder, Quantum Thursdays is geared to our undergraduate and graduate communities to bring more awareness around quantum information science, the research being done at C2QA, and then also the different career paths that you can take in QIS. And so before I introduce our first speaker, I'd just like to do a little housekeeping. All Q&A will be managed through our chat function. Margaret will take breaks, so when she can, or I'll remind her to answer those questions in a timely manner. And then if everybody could remain on mute as we're going through the lecture today. And so today I am pleased to introduce Margaret Martonosi from Princeton University. We have generally focused on a lot of material science, devices, etc. And Margaret's is a computer scientist, so we get a little bit of a different perspective than quantum today. And she'll be speaking to us about closing the gap between quantum algorithms and hardware using compilation and architecture. So Margaret, I will turn it over to you.
Wonderful, thanks, and good morning and good afternoon to everyone. It's great to be here. And here we go. This is work, I should say, that reflects research in my group over the past few years, including my PhD students that you can see named here, as well as a broader collaborative community that I've been fortunate to be a part of. So I think as was mentioned, I'm likely to bring a slightly different perspective to quantum than some of the other talks because of where I sit in the stack, if you will, regarding quantum. This graph helps to sort of orient you around the space. So when you think about quantum computing and you go back over the past 30 years, I think there were exciting algorithmic observations early on about the opportunities for potential exponential speedup in cases like Shor's factoring algorithm. But throughout it all, there was, for a long time, a sense that there was a gap between what the algorithms needed and what the sort of most capable buildable quantum machines of that time looked like. And so this yellow line is very much of a cartoon. We'll talk more about benchmarking later. But for now, it's intended to show, roughly speaking, some aspect, some summary of the capabilities of quantum architectures over the years, and sort of understanding roughly where we are in terms of qubit counts. As we go forward, and so clearly there's literally orders of magnitude difference between what something like Shor's factoring algorithm needs in order to be useful at scale versus what we can actually build. As we go forward, what we can see is that over recent years, we've seen that hardware really has progressed well, and we can see that we're both increasing quantum volume and also sort of showing other demonstrations of how our QC hardware expertise has improved in terms of improved noise characteristics, improved connectivity between qubits, and so forth. So that's good news. And in fact, that may say that this slope of this yellow line, note that this is a log scale, could tilt upwards. We don't really know where we're going on any sort of strong trajectory, although we develop a better sense of that as we go forward. So then let's look at the algorithm side of things. There's also been progress there. So from those early algorithms that really captivated us and brought the field forward, there's been considerable algorithmic progress over the years, and that includes increasingly new breeds of quantum algorithms that are oriented around lower qubit needs than the sort of original ones like Shor's, and often hybrid iterations of quantum and classical phases. These don't tend to offer exponential speedup, but they do serve as both promising demonstrations and also potential use cases much earlier, much sooner in time. And I think one of the things that people often find surprising is the number of different quantum algorithms that are sort of out there. There's a quantum zoo that you can go look them up in, beyond the ones that get most of the press, if you will. So where are we? We're in this area. We've been in this NISQ era for almost, for over 5 years now. And it's an area where more work is needed because the blue and the yellow still don't meet, there's still a gap. And so what we're seeing is a sense that, you know, algorithms may continue to improve, hardware may continue to improve, but in the end, we're going to need things that sit between algorithms and hardware that can help shrink that gap and move the feasibility and the usability point of quantum systems sooner. And so I'm a computer architect. I sit at the hardware software interface. I've been doing work in computer architecture for longer than quantum computing has really existed as a thing to think about. And on the classical side of my work, we've looked at different ways of exploring this full stack space. And in the quantum side of my work, similarly, we look at ways in which thinking about quantum as a full stack from algorithms to circuits to qubits can improve how they work, improve the virtuous cycle that we're in with noisy intermediate scale quantum, and get us sort of going closer both towards useful quantum in general and fault tolerant quantum as one particular aspect of that. So today what I'm going to do is I'm going to talk through a few examples with my computer science and computer systems hat on to talk through ways in which we've taken on this co-design opportunity in my research group. And each one of these is sort of a little vignette. And then going forward, towards the end, I'll sort of pull it together and talk about how they fit together. So the first one of these is about managing capacity challenges on current quantum computers. And so the basic gist of current quantum computers is they're not big enough. That's a big part of what that previous gap that I talked about referred to. They're not big enough, so there are capacity challenges. There's also noise challenges. They don't have high enough fidelity when they're executing operations. So the idea in this work is instead of taking the algorithm and only running it when we have a quantum system that is large enough and capable enough to run the whole thing, what if we could cut it into parts, run the subparts on smaller quantum circuits, and then sew those results back together again? If you have done any work in your research life on field programmable gate arrays or FPGA systems in the classical world, you may know that actually when we're running things on FPGA emulators, we'll often take a large classical circuit, cut it into pieces, run it on the FPGA that can fit it, and then sew results back together again. So this approach is intuitively appealing, but here's the challenge. When you cut a quantum circuit into subparts and try to sew it back together again, that reconstruction time, sewing together things at the boundaries, is time and resource intensive. And in fact, it's actually, there's an exponential cost associated with that sewing back together, that reconstruction time. So what we did in this work was take a theoretical proposal about circuit cutting and explore ways to take that theoretical proposal and make it real to demonstrate practical circuit cutting tool chains that can actually beat classical simulation in runtime and can beat NISC in terms of both fidelity and circuit sizes. And we presented this at a conference in the computer architecture and systems community, ASP+, about a year ago. So the way this approach works is, here's an example of a quantum circuit. We can cut one edge in that quantum circuit where the X is, and it will be viewable as two quantum circuits, the upper and the lower. To deal with the reconstruction, we need to know how to sew things back together again to account for the state issues in the red highlighted parts of the circuit once it's been cut on the right-hand side. So the basic gist of what we want to do is we want to select the cut points. Where do we put this X or these X's? We want to run the sub-circuits either on a simulator or on a small NISC platform. And then we want to reconstruct to sew things back together again using these classical computation techniques to reconstruct the state. There's actually a fair amount of research to be done just in what are the right cut points in order to improve the fidelity and reduce the reconstruction time. And so I'll show you just a snippet about our results here. So what we have here is some results that show the ability to get significant 60x to almost 9,000x speed ups over a classical simulation baseline. So what are we doing here? We're saying if you have a circuit that's bigger than any existing quantum computer that you have access to, then your only other option prior to our work would have been to simulate it classically. And what our work says is, instead of classical simulation, why don't we take that large circuit, cut it into smaller pieces, and then run those smaller pieces on the machines we do have and sew them back together again. And so these graphs show this cut QC for a range of different algorithms. Grover's algorithm, the quantum supremacy algorithm from Google, and some others. You can see them color-coded here. For each of the scenarios, classical simulation is shown in the black line that's here. And then what we do is we show time on the y-axis in, again, note the log scale here, and we show the circuit size on the x-axis. So this is a 10-qubit quantum computer that we're running on. And by the right-hand side, we're doing a 34-qubit version of the benchmark, right? So basically, when it's a 34-qubit version of the benchmark, or 35 for some of the other graphs, we are having to cut multiple times in order to be able to fit it onto the 10-qubit resource that we actually have. So you can see we do this for a 10-qubit quantum computer, a 15-qubit quantum computer, a 20, and a 25. So some insights. Well, first insight is this speed up, that it works. You can see this by saying, usually the colored lines, which are our experimental results, are below the quantum simulation line, the black. So that says usually we're offering speed up. Lower is better here. So good for that. Some other insights, not surprisingly, a densely connected circuit is harder to cut because more reconstruction more cuts are required to actually partition the circuit into smaller chunks that will run on these small QCs, and more construction is required after the fact to put things back together again. Also, not surprisingly, larger quantum circuits generally require more post-processing. The other thing is that as you move through these different options, as you move out towards larger quantum computers, that generally improves the runtime, but there's some diminishing marginal returns. So for example, the quantum supremacy algorithm actually has the same cuts for both the 20 and 25 qubit machine, and therefore you don't get any extra benefits from having the 25 qubit machine because you can only partition in certain ways. So that's good, that's promising. We wanted to take it further. We actually wanted to push these advantages even further. And so one of the things that we looked at was, what if you don't need perfect state reconstruction, but you instead want to have essentially a blurred probability landscape by combining and tracking the sum of amplitudes for a group of quantum states. So basically, we want to be able to zoom in and only get good definition on a part of the space in order to save time. And so that's what these graphs show. These graphs show that instead of running circuits of up to 35 qubits, which you saw in the previous slide, now look at the x-axis, you can see we're able to get out to 100 qubits. So that's beyond what's considered the sort of classical simulation limit right now. We're able to do so by zooming in on the part of the state that we have decided is worthy of our attention right now. You may not always know how to do that dynamic definition, but if there are problems that can be framed in a way where this dynamic definition is useful, then it allows you to greatly scale out the kinds of quantum algorithms you can run. So Some insights here. We expect that NISC devices are going to gradually improve in fidelity and in size, so that we don't have to cut into as small, tiny pieces as before. And that will allow us to really get out beyond the classical simulation limit even more convincingly. And then CutQC allows us to sort of query the output of these very large circuits with high fidelity. So I gave a link to the paper on the previous slide, the link to the GitHub, and a full video that's just about this talk, this paper, is available on my students' webpage that you can see the link for here. So that's one vignette about cutting large algorithms, large problems to fit on current NISC machines. Second thing I want to do is to go up the stack and talk about how can we tailor algorithms to think about modern NISC machines instead of sort of doing quantum algorithms in isolation from real implementations. So here, we're going to talk about a particular set of experiences that we've had with one space of quantum algorithms. In particular, oh, thanks for adding the link. Great. I'm also happy to share a PDF of these slides if Diana has a way of sharing them out with attendees. This algorithm, this part of this talk focuses on Hamiltonian simulations. And the idea here is to do a set of strategies on how we think about these simulations in order to mitigate errors. And Hamiltonian simulations are useful across a range of possible QC applications. So they're sort of a broader class than just one particular benchmark. They have two issues that we have to take on. So one issue is the algorithmic errors, and the other issue is physical errors. So let me dig in on each of these. Hamiltonian simulations are really about simulating a continuous evolution of a state, and yet we're going to do so using discrete operations. So we would like to have time be truly continuous. Time is not continuous. And so there are these discrete operations or trotterization, and therefore there are trotter errors that are incurred when we map the problem onto a digital quantum computer. The second set of errors have to do with the physical errors of potentially noisy gates. And these physical errors are clearly important in the NISC era. They will remain important in the fault-tolerant era, simply because even if we have a fault-tolerant machine, error correction is likely to take some time, and therefore high error rates are likely to lead to longer runtime. So it will still be relevant, just sort of a different metric. Okay, so what this work does is it mitigates these errors in multiple ways. In essence, it takes the poly terms that are key to this kind of simulation. It groups them into groups or cliques that are commutative. And it says, hey, if they're commutative, there are different orders in which we can do them. And we should think about which is the order that will lead to the lowest algorithmic error. And then subsequently, we can think later on about other kinds of error mitigation, like the physical error. But for the bulk of what I'm going to talk about here, I'm talking about using different orderings in order to reduce this green, this trotterization error. And in particular, we're going to look at how different sorting strategies, different ordering strategies, when we have a choice, when something is commutative, that will actually allow us to maximize the gate canceling within the group in order to reduce the error. This was presented at another computing conference, International Conference on Rebooting Computing, about 6 months ago, where Teague's work received the Best Paper Award. So how does this work in a little more detail? So this is basically a background slide. The high-level takeaway is that we're going to take this application level information into how we compile the circuit. So we are trotterizing. That leads to the error term that I mentioned, and the goal is to minimize that error term. And so we're deciding how we can order the different terms in this box in order to reduce the trotter error that's going to remain. And in particular, we're going to look for gate cancellation as the strategy for doing that. So at the application level, we have something that looks like this. And our goal is to determine the right ordering that's going to then sort of be output as a circuit that will reduce error. And so we've used different heuristics for how to reduce that error. The one that we look at is a traveling salesman problem that basically produces circuits that contain fewer C0 gates and therefore lower error as a result. So what we have on the left-hand side here is time and number of C0s. And you can see the gate cost for taking that same quantum simulation and using different techniques on it. So our work is the lower blue line here. And again, lower is better because we're doing gate count here on the left. So for an average accuracy threshold, our approach actually results in roughly 40% fewer C0 gates. Then you can actually run these on real NISC hardware and see how they do. What we see here is the notion of how MCTSP basically hangs in there or reduces the variance on real runs as well. So we did encounter cases where the different orderings sort of did unusual things in the NISC realm relative to the more theoretical realm because of things like how circuit depth varies and so forth. But MCTSP tends to strike a good balance in terms of both error rates, variance, and so forth, and represents a good approach overall. So onward, one more of these vignettes about how we can take an algorithms and computer science way of thinking up high and also consider the realities of current quantum computing error rates and implementations and capacity limits down low and try to co-design between these different levels. So in this case, the next one I'm going to do is about architectures and organizations for future quantum computers. Okay, so I don't know what your backgrounds are. I don't know how many of you are physicists, material scientists, mathematicians, computer scientists, and so forth. Often when I go into the world and I say that I'm a computer architect, people think of buildings. I don't do anything to do with buildings. Computer architecture refers to the subtopic area of computer science that looks at how to interface between hardware and software in computer systems. And in particular, a key attribute that was first sort of studied well over 50 years ago and has carried us forward to this day is the notion that if we have enduring hardware software abstractions, it will help us navigate complexity over time. What does that mean? Computer architecture as a term was proposed in the 1960s by IBM because IBM wanted to be able to have different hardware implementations of their supercomputers at different price points and yet have the same software run on all of them. Go forward a few decades, the x86 instruction set from Intel is a great example of an instruction set that has been sort of enduring over literally decades. If you're running this talk on an Intel-based laptop, you are making use of that instruction set, even though it may be older than some of you. It's decades old. So across different types of implementations and different types of machines, one of the great advantages of computer architecture is thinking about what that interface will look like so that it can last over time. Okay, so now let's think about quantum. Quantum is at this incredible sort of space where we're just now thinking about these abstractions that are decades old on the classical side of things. And we're saying, what should the basic vocabulary of a quantum computer be in order both to have some hope for enduring abstractions over time and also to have the right kinds of behaviors now across different implementations? Wouldn't it be nice if I could write an algorithm once and have it run on both supercomputing and ion trap machines in a sort of best in show way so that the best attributes of each particular implementation shine through? And so this particular vignette that I'm going to talk about now looks at that. It says, how can we design the right instruction sets for quantum computing machines? And we've actually done several papers in this line of work. So I'm not going to be able to talk about the full space of what are called instruction set architecture or ISA choices. But what I am going to talk about here is one that has to do with a fundamental trade-off that we see in quantum computing machines today. Namely, if I asked you to do one thing well, you'd probably get really good at it. If I ask you to be really good at two things, you can probably be really good at two things. If I ask you to be really good at 100 things, eventually you reach your limit where you can't be the world's expert on 100 things. Instruction set architectures and quantum computers have this kind of a trade-off as well. If we have a small and limited instruction set, it makes it easier to be good at that small and limited set of instructions, and it makes it easier to do the calibration that is increasingly a large part of what quantum computers spend each day doing. The estimates are that calibration time is as much as a third of the uptime of the quantum computers that are cloud connected right now. So we are looking here at how can we come up with a set of fundamental operations that keep the calibration cost manageable while also being expressive enough to run useful applications. And in particular, that expressivity says that if we have exactly the right vocabulary for things, we ought to be able to run things with lower error rate. So there's this trade-off of the error when we run, the calibration time beforehand. I have this bullet down here that maybe is sort of just for the computer architects in the audience, but I will say that about 40 years ago, there was a huge debate in our community called RISC versus CISC. And so if you are running things right now on an Intel-based laptop, you're running things on what's called a CISC or complex instruction set computer. On the other hand, there are RISC processors out there that are called reduced instruction set computers. They made very different choices about expressivity and how to implement the same software. And so if you happen to be familiar with something like RISC-V, which is a large open source hardware movement, that's an example of a RISC processor that's out in the world today. These kinds of choices and balancing acts have been going on for decades. Our work was to bring that into the quantum computing side. So, in essence, you can sort of take different examples of implementations and the instruction set choices that they made. So IBM, in exposing things to software, as well as the early Rigetti machines and Google systems, tended to offer a single type of 2-qubit gate. Great for hardware, very easy to calibrate, but pretty restrictive for the application. Pretty hard to compile to such a teeny tiny instruction set. It increases the instruction count, increases the likelihood that errors will compound as the program progresses. So on the other hand, there are instruction sets with continuous 2-qubit gates, much more choice. You can see some examples of that here. From the application side, this is awesome. Very expressive, lower instruction counts. Compilers love them, application folks love them. hardware is like, that's an awful lot to calibrate. Each of these gates has this continuous aspect to it that makes it even harder to calibrate. So you can see the trade-off that's forming here. And the research questions for us were, how do we strike this balance? Is there an instruction set? Is there a vocabulary for these machines that's highly expressive for the applications and also good enough, easy enough to calibrate? Are there a small number of 2-qubit gate types that we can sort of preset rather than that continuous option that will be enough expressivity for NISC applications? So basically, can we strike the right balance between the upper and the lower? And then when we are at that balance, what will the calibration overheads look like? So again, we did this study fairly empirically. We took a configurable tool flow where we could tell the tool flow you have this vocabulary to work with, or you have that bigger vocabulary to work with. And we ran this using realistic noise simulations of Rigetti and Google systems. And we varied between 4 and 8 different gate types to consider different amounts of expressivity and fidelity. So you can think about this colored landscape here as what are the gate types that we considered in terms of the C phase angle and the I swap ish angle down here. And you can see the green boxes that were the different operating points, the different gate types that we either included in the vocabulary or not. So the answer to those questions from the previous slide was that you get considerably higher calibration time when you go out to these multiple gate types compared to the C0, the simplest, the single gate type, but still manageable on current systems. The benefit is it's 2 orders of magnitude less calibration overhead than a continuous gate set. So let me go back a slide. I said this bottom box is good, but high calibration overhead. I said the top box is easy to calibrate, but too restrictive. What we've done is we've come up with a middle ground, much easier to calibrate than the lower stuff, much easier to compile for than the upper stuff. And in fact, 2 orders of magnitude less overhead than the continuous gate set that's the lower box from the previous slide, and higher calibration time than the upper box. And so the paper goes into more detail, but it basically offers this middle ground that shows sort of huge improvements in fidelity, instruction counts, and therefore fidelity compared to the single gate type. So double the fidelity, much less overhead, happy medium, yay. So that was 3 vignettes. I'm into the 4th one. Oh, question came into the chat. What about restrictions on implementing different gate sets? Yeah, so calibration is really the last step in sort of implementations more broadly. We went with a set that seemed quite implementable, and then the question was, do you really want a continuous dial on the implementation, or are you willing to have certain set points that you implement for? And in choosing certain angle set points, it actually greatly improves calibration time, which you can think about as greatly easing implementation. Thanks. So the last of these I'm going to talk about is benchmarking. So all of these have been about how do we operate at that area between algorithms up high and implementations down low. What I'm going to talk about now is how do you know what's good or not? How do you decide on the performance, the outcomes, the results of making these different balancing act choices? So in particular, the first slide that I had in this talk had an x-axis that was just qubit count. And I sort of said, maybe that's a good kind of shorthand for the capability of the machine. But I'm sure if you've been coming to these talks for a while, you're more sophisticated than that. You know that there's actually an awful lot that matters in thinking about the capability of a machine. So we want not just to have one vendor say we have this many qubits and another vendor to say, haha, we have more. We want the ability to actually envision how different useful applications might sort of succeed or not succeed on these different implementations in order to use that as a metric for which direction we should go as we're evolving this field. And again, because I sort of come from classical computer architecture, I will say that for many years, we have used benchmarking in the classical side of things to gauge the speed and the capability of different computers. So for example, there's a famous set of benchmarks called the spec benchmarks that a consortium of many different hardware vendors come together on, and they say, we agree, this is what we're going to report our performance relative to, because they sort of span the space in a useful way. Put the computer through their paces, say what the spec mark rating is, and that's a way of giving some shorthand for the overall performance and generality of the machine. And so we're trying to get to that in the quantum computing side. Now, what does quantum computing need? One thing that it needs are benchmarks that are scalable, because if we made a benchmark that only needed, say, 4 qubits, then pretty quickly that would not show any benefits to building out larger systems. We want benchmarks that show benefits even as we increase the capability of the systems. Second of all, we want things that are fairly application oriented. We want to really have a North Star of, are we going in a direction that will lead to useful applications eventually? And third of all, we want them to be distinct and diverse so that we can know, oh, okay, this machine is really good on this type of calculation, and that machine is really good on that type of calculation, and understand which machines are good at a particular specialized calculation and which machines are more general. Not that there's a single right answer, but that it's always useful to be able to sort of navigate in a design space in that way. My PhD student, Teague Tomesh, along with this quite large set of co-authors, led the charge on proposing a scalable quantum benchmark suite called SuperMark. And so the idea of this is to achieve scalability in a parameterized way. And so that checks off this first bullet, and to be application oriented, to pull from a range of domains like QAOA, variational quantum eigensolver, and so forth, in order to sort of show that application orientation, and also to demonstrate ways of showing the benchmark results that are oriented around particular sort of feature spaces rather than kind of performance as the only metric. And so these feature vectors are going to be a part of sort of key to the equation. And you can see that the feature vectors have to do with different attributes that you might measure about a particular quantum application, and it's run. So what we did here is we took a QAOA benchmark and we ran it on a bunch of different implementations. You can see them here. Some superconducting implementations and some trapped ion. And the bar chart shows the results for the different runs in terms of their feature vector scores. And then the scatter plot down here shows how correlated that is with a feature from the quantum program profile. So sort of stepping back a bit, one of the things that we would like the benchmarks to do is to be predictive. That if I have some idea about a machine's attributes, I should be able to use these kinds of feature vector spaces to predict how well a given benchmark is going to do on that machine based on the feature vectors that we see. And so where you see good correlation between the benchmark score and a particular attribute, that says that these feature vectors are doing a good job in acting as predictors forward of behavior. And that means that we can get to what for quantum computing hasn't existed yet, but for classical computing is kind of the standard and what we consider in our field to be the holy grail, which is we want to be able to sit at a moment in time, February 2022, and use the currently available machines to predict something about the future available machines. We want to be able to predict performance before a machine exists. So you can either use benchmarking to evaluate the performance of existing machines, or you can use benchmarking to predict, gauge, and design for the performance of some future machine. Evaluating the performance of existing machines is fine. Using it as a predictor for future machines is really where we need to get to in order to guide design processes in a well-informed way. And so that's what these kinds of benchmarking techniques are designed to do. And I guess the last thing that I'll say on this slide is that quantum computing is in a very sort of nascent part of its evolution. And so it's highly unlikely that the benchmarks we've picked and the feature vectors we've picked and so forth are the right ones for forever, right? This is going to be an evolutionary process where we're going to keep learning what are useful feature vectors, and we're going to keep sort of learning what are different benchmarks that we should be folding in to put different types of machines through their paces. And so we see this as an iterative process where we can take some of the application profiles as we build them out and actually circle back and improve the benchmarks as well. So zooming back out again, I've given you four examples, different vignettes where we go from application and algorithm down pretty close to hardware. I'm not designing individual qubits. Nobody in my group is designing individual qubits or material studies. We're a layer above that, but we're saying if systems get built that have roughly the attributes we're seeing right now, but maybe scaled out a bit, how can we best connect the different layers? How can we learn from the different layers to inform design attributes and design decisions that we're making elsewhere? And so with that as the mindset, I always like at this point to take a trip in the Wayback Machine. 1950, I was not around in 1950. Many of you were not around in 1950, but here's what classical computing looked like in the 1950s. Algorithms way up high, folks were thinking about things that were way beyond what existing computers could do. Turing was asking the question in 1950, can machines think? He was thinking about artificial intelligence in 1950, even though what you're looking at in this picture was like a single floating point multiplier that was bigger than those people, right? So he was doing algorithms that were way beyond the capabilities of current machines. Under the covers in the 1950s, we had implementations that were built out of vacuum tubes and relay circuits. In 1950 itself, we had just barely invented a transistor, but it wasn't being used in computing yet in 1950. That would take a few more years. It was being used in radios in 1950, and it would be by the end of the 1950s that transistorized computers were built. So one thing that we can learn from this is it is completely okay for our algorithmic thinking to be out ahead of what our machines can currently do. It is also completely okay to be looking at initial implementations that might not be the ultimate winners. If you were to pick a front runner technology and try to pick a winner in 1950, you might not have picked, you probably wouldn't have picked that the transistor be the winning technology in 2022. You might have picked vacuum tubes. And so I think we have to do work that can navigate technology changes fairly smoothly as we come up with different innovations that are ready for it. The other thing about the 1950s is there's a big white spot between algorithms and the assembly language that was used to program these systems. And over time, we filled in that white spot with the whole field of computer science and computer systems layered in there. Programming languages and so on and so forth. Quantum computing is in a very similar state. Algorithms up high, qubit implementations down low. No clarity yet on what the winning technology will be, and a big gap between the capabilities the algorithms want and the ability of particular implementations to deliver those capabilities. What today's classical computing space looks like is something like this: semiconductor transistors down low, VLSI circuits, gates, architecture, compilers that translate from algorithms through high-level languages to an architecture, and an operating system interposed in there as well. So we came up with this layering strategy literally over decades in the classical computing side of things. And the interesting question is, like, what are we going to do on the quantum computing side of things? We have over here a to-do list, if you will. We need high-level quantum languages, compilers. We need error correcting codes. We know, to some degree, we know the to-do list. What we don't know yet is going to be, what's the right layering strategy? Where are abstractions going to work? Where are they not going to work? Where are we going to have to share more information in order to move forward? So, so classical and quantum here in comparison. And I think what I wanted to end with is this notion of the stack not organized in terms of what you see here, which are strict layers that know precisely what to communicate up and down or not, but rather information flow that's going up and down. So in this view of the same stack, we see algorithms up high, we see physical qubits down low, we see compilers sitting there in the middle. But in the quantum view of things, we believe, and all of our results, everything that I've talked about today shows that you really need to still be ready to have information flow up from implementations and information flow down from algorithms. This is different than classical computing right now. When you write a Python program, you don't need to know whether your computer is using bipolar transistors, CMOS transistors, or something else, because of the abstraction layers that shield you. You don't need to know the error rate of the DRAM when you're writing that program. In quantum, there's still a need for more information flow because we're at a different part of the evolution space. So we can get to near-term successes faster if we're willing to accept information flow up and down the stack as a key part of what we do. We believe, and we have shown, that using application and hardware-specific information to inform the low-level quantum system design can get us orders of magnitude advantages that will get us to quantum supremacy faster and for a wider range of applications and implementations. Another thing that I want to highlight is the degree to which quantum systems don't sort of sit in isolation, but rather quantum systems sit alongside a classical coprocessor. And there needs to be much more attention placed on this interplay between the classical coprocessor and the physical quantum machine, especially when you think about things like QC that I talked about, but also things like VQE and other places where there is a classical phase to the algorithm alternating with a quantum phase. So what I've tried to show here is that while we're working towards filling in the gap between algorithms and physical qubits, there may be a considerable amount of evolution that happens as we go forward. I have found that it's just an extraordinarily fun area to work in as a computer scientist, as a computer architect. And I've also found it incredibly rewarding to work with my colleagues who are either quote unquote above us or quote unquote below us in this stack, because it is that interplay, it is that co-design that makes things really effective, especially when we're talking about the next 5 or 10 years. So with that, I'm happy to field a few more questions in the time that remains.
And Margaret, just to remind me, we did have a question here. What about restriction limitations on implementing different gate sets? Did we address that one already?
Yeah, I did.
You did. Okay, great. So any other questions, please feel free to put them in the chat function.
Oh, and I should take this time while people are pondering their questions to re-acknowledge my grad students, Wei Tang, Teague Tomesh, who I think are both here on the line, and also my now graduated student, Prakash Murali, whose work I was trying to do justice to today. And I fully reserve the right to phone a friend and ask them to come off mute and answer your hard questions. So feel free to ask either easy questions or hard questions as they occur to you.
We're getting some thumbs up, inspiring closing statement.
I'm gonna go into professorial mode here for a minute. Can you use, I think you have thumbs up keys on your Zoom. Can you use the thumbs up key to tell me if you would consider yourself to be from the, we'll call it the down low part of quantum. So you're a physicist, a material scientist, something like that. Okay. I love that it's a mixture of like the PIs of the center along with students and so forth, all doing that. Okay, how many algorithmicists do we have? Okay, I think I saw some, but not as many. How many generalists? How many full stack quantum folks do we have? I'm going to raise my hand for that one. Okay, some tons of materials, folks. Great. I would love to hear your thoughts on what are the pieces of information. We have a question.
Yeah.
Is the expressivity to calibration speed trade-off for gate sets? In the expressivity to calibration speed trade-off for gate sets, optimal control would be all the way on one end. What are your opinions on optimal control? So I think this work was informed by our collaborators who are in the business of building real machines, who had a certain calibration approach that was sort of baked in, and then we were working around and with that. So my hunch as an architect is that this operating point where you're not trying to be fully expressive, but you are trying to execute effectively at a smaller set of set points is likely to be more achievable and B, more time efficient. And so around each one of those set points, you may choose to use different control strategies. But I think the ability for a gate set to work effectively across a very broad operating range is just intrinsically more challenging than if you can pick a few selected set points for it to operate at. Looks like Rob has his hand up.
Yeah, thanks, Margaret. That was a great talk, especially for someone who's very much bottom of the stack. Like I felt like I at least appreciated, even if I didn't fully grok all the stuff that you were talking about. Maybe one comment and then one question. So the bit about parameterized gates, I think if you tell me you want me to do that and have a continuously parameterized gate, I don't have to have 100 discrete settings that cost 100 times the calibration time. Like if I've done my job right as a hardware designer, I should have one calibration that's sort of fixed cost that lets you have access to all the different settings. Like, I mean, in the end, in most of these things, we're implementing like some amplitude or phase control of a classical signal to scan those angles. I should be able to do that very nicely, right? And so it might be interesting to think about if you weren't sort of saying there's a one-to-one trade-off of number of gates in your instruction set to calibration time, how much could you gain? So, but then my other question was about the cutting of the circuits. Go ahead, maybe.
I was going to say that that's good to know because I think it would be interesting to do follow-on work with sort of a different set of assumptions and see what we came to with those different assumptions.
Right.
And C2QA is always looking for these kinds of vertical slices that can demonstrate the value of that kind of information sharing. So let's put that one on the to-do, on the mental to-do.
Yeah, I mean, it would be great to chat a bit more and figure out like how many different settings would give you how much gain in efficiency or something. The other thing that seems like a really neat area to think about would be like in the circuit cutting. Have you thought about what happens if we have some error correction or error detection that plays with that? What about I do the first part of the circuit many times till success, and then I do the rest? Does that work?
I think there's a lot of promise there, and actually we have some subsequent work on different ways. So I talked about dynamic definition as sort of one way to blur a state space in order to get some speed. We have some other approaches that sample the state space. It's not quite the measure and then move on, but it is sort of a sampling of the state space in a different way with some of those strategies in mind. So I think that's a stay tuned thing because we are working sort of in that area. And then the measure and move on, where the application supports that, that has nice attributes for other purposes as well. So in work I didn't talk about today, one of my postdocs who's now a Rutgers faculty member did work on how would you actually build a debugger for a piece of quantum software. And that also has this notion of, clearly measurement collapses the state, right? So that's sort of a big problem for traditional ways of debugging, but had ways of state sampling in order to try to discern some of what was going on before moving many of the shots forward.
We did have some more questions come in. You see them, Margaret, or?
Yeah, I'm picking what I can answer in a minute.
I know. And if everybody could just put on your videos for a minute, it would be great to get a shot of everybody while Margaret's going through.
Instruction sets with universal control, but errors due to energy constraints or other issues. How do we quantitatively put this into the trade-off considerations? I'll just say that with a smile because, full employment for computer architects. I've been doing computer architecture for 40 years now, and it's exactly this stuff that we've been working on as trade-offs for forever. And so there are ways to bring in other dimensions. I think in the quantum side of things, we're still mostly focusing on the real basic fundamentals. But yeah, you could come into other optimization approaches or design trade-offs as well. What kinds of dynamic definitions cannot be accurately mapped? How much of an issue is this for prospective quantum computing applications? So I'm wondering if, there's Wei. I see Wei now that his camera is on. I think I'm gonna bounce this to Wei because I have an answer, but I think he'll have a better answer. Wei, do you wanna?
Sure, yeah. So when we do dynamic definition, what we're really doing is, so first of all, the idea behind dynamic definition is that when a circuit gets large enough, you have way too many number of full states because you simply have 2 to the n number of full states to even record if you want to analyze them in full, which becomes impossible. It's impossible to do it via classical. It's impossible to do it via quantum. Because first, you don't have enough space to store even those numbers as floating point numbers. Second, that's the main memory bottleneck to deal with such a large state space. So what we do in dynamic definition is we group certain states together, and instead of tracking the probabilities of the individual states, we are asking ourselves the question, what's the sum of probabilities for all of those states? So the idea is simple, is that if a lot of states are not of interest to you, meaning they have extremely low probability amplitudes, then their sum is probably also of very low, even zero probability amplitudes. And they can be quite rapidly get rid of because you're basically saying we're not interested in those states. And as far as if your application, the output of your application, it focuses on its probability on a few states as the quote unquote solution states, dynamic definition algorithms helps you extremely quickly to locate what those states are, and while quickly discarding the other states with nearly zero probability amplitudes. However, for applications such as the quantum supremacy experiments that Google did, their probability amplitudes are much more distributed among all the states, and dynamic definition can be quite limited in that regard. However, it's impossible either way to analyze such a large space with very distributed probability amplitudes anyway, even if you have a large enough quantum computer, because then you will need maybe exponentially many more shots to even converge to a meaningful probability distributions. And you will never have enough capacity to store those probability amplitudes as results anyway. So yeah, for the meaningful applications that we're targeting, dynamic definition will get you there pretty quick, pretty fast.
Thank you. I told you he'd have a good answer.
You certainly did tell us that, Margaret. Thank you for the wonderful talk and all of the questions and after talks. Are there any other questions? We don't want to cut anyone off. We know we're a few minutes beyond the hour, but if you do have additional questions, one more maybe, and if it goes over that, we'll put them in the chat and we'll try to get an answer for you. Diana had to step away to another meeting, but thank you all for holding on. All right, I don't see any hands up and I don't see any additional questions in the chat. So we do thank you for joining us for our inaugural Spring Quantum Thursday session. Do spread the word. These will be happening throughout the semester. So we are grateful for you joining and we hope to see you again soon. Margaret, thank you so very much.
Thank
Final
you.
words. Final words, Margaret, all for you.
Thank you. Have a great day. I hope you're all enjoying your work up and down this quantum computing stack.
Great talk. Thanks, Margaret.
Thank you.
Bye, everyone.